Good evening, everyone. It's with great pleasure that I'm able to welcome Kas Oosterhuis as our CCA architecture lecturer this evening. Tonight's lecture is part of a special series of events called Seeing Orange, Dutch Design Week at CCA. All of the events are listed on postcards that we have that are by the entrance to the lecture hall. And I just also want to announce that tomorrow evening that there will be a kickoff event, reception, and exhibition at the New Black, which is at 1999 Bryant Street. It's Bryant and 18th. That'll run from 6 to 9 p.m., to which you're all invited in San Francisco. Dutch Design Week is being co-sponsored by the Consulate General of the Netherlands, and I want to thank them and Jennifer Cattell and her colleagues for all of their support, for working with us to form a stronger cultural global partnership to enable events such as this one this evening. We've been doing this now for a few years, and we've been able to bring a number of Dutch architects and designers to CCA and have events throughout the city. Kas is a professor of architecture at Delft University, as well as the director of Hyperbody and the Protospace Laboratory for Collective Design and Engineering. His research and teaching has been focused in the areas of interactive architecture and the real-time behavior of buildings and environments, the concept of living buildings, as well as parametric design and file-to-factory production. His firm, initially established in 1989 in Rotterdam, was later renamed ONL for Oosterhuis Lénárd, in partnership with Hungarian visual artist Ilona Lénárd, who's with us this evening as well. The work of the firm and the experimental nature of Kas's research pushes the boundaries in many ways of typical design practice in the Netherlands. In his most recent book, Towards a New Kind of Building, A Designer's Guide to Nonstandard Architecture, published by the NAI in 2011, Kas speaks to the paradigm shift from the standard to the non-standard and the shift from static to dynamic forms of architecture. The firm's works have received many honors and awards and have included such notable projects as the streamlined and whale-like CET project in Budapest that received an Autodesk BIM Experience Award, and the earlier Hydra Saltwater Pavilion that received a Gold Award for innovative recreational projects and a nomination for the Mies van der Rohe Award. The latter building was one of the first contemporary projects exploring the physical and perceptual conditions of fluid space and the dynamics of an internal sensory experience, and was part of the complex at the Delta Works in the Netherlands that was done in concert with the Freshwater Pavilion by Knox Architects. Other projects have included the Liwa Tower project in Dubai that synthesizes architectural form, structure, and ornament through an elaboration of a slightly curved perforated building skin, and the Hessing Cockpit Building and Acoustic Barrier projects in Utrecht and Vienna. The former was the recipient of a number of awards, including the National Steel and Glass Awards and the Dutch Design Award for Public Space. These projects are focused on transforming infrastructure into dynamic models for architectural parametric exploration and intervention. These and many other projects reveal the firm's interest not only in speculation, as one might project toward interactive design futures, but also a strong commitment to innovating with materials and technologies and embedding these within real contexts. Kas's research and design work and the work of the firm has been published extensively and exhibited internationally in many prominent venues, including the Pompidou Center in Paris, the FRAC in Orléans, the Venice and London Biennales, along with exhibitions in Shanghai, Beijing, Frankfurt, Munich, Brussels, Dubai, and many others. He is a graduate of Delft University of Technology, where he's a professor of digital design methods, along with directing the Hyperbody Research Group and the Protospace Lab. We're really happy to have Kas with us this evening to inaugurate our events as part of Dutch Design Week. Please join me in welcoming Kas Oosterhuis.
Well, thank you, Ayla. I'm wondering how much of your time how much endurance I can ask from you tonight. I prepared a lecture of, I think, more than 1 hour, so, but let's see. What I usually do in lectures is to have an interactive setting. That means that I usually have a second screen, and then you can send your tweets. And then I read the tweets, and I can respond what you are thinking. And it's a kind of interactivity I like. So I didn't set it up tonight, but if you want to say something while I'm lecturing, please do. Yeah? Please interrupt me, and please start a discussion while lecturing. I like that much better than having questions afterwards. So let's see if you have the guts. The new standard, it's almost a contradiction, because I'm not for standards, I'm against standards, because standards are actually built when there is a relation between two things, two people, or two situations. Then you build actually your own customized standard. So, but the new standard is meant to be that kind of standard, which is also referred to as non-standard, that actually includes all the other forms of standardism that has been around for the years. So the approach to try to have one standard that fits all is really the wrong approach. And I will show you that through our approach to building. You will hear from me a lot of words like these, but so I won't read this for you. But there are words that are completely new in architectural language. Some of them, or many of them, are included in this book. The main system of this book actually is 4 chapters. One is tag that body. Tag that body means that I see architecture as a body. I see buildings as a body, having a body, something that is consistent and integrated. And then I say, make that body, that's the 2nd chapter. How do you make things? So I think the construction methods, especially CNC construction methods, are purely essential to have in the design phase. And that's exactly what is missing in most of the buildings you see around, that they are designed. It's very linear process designed, and then they are tendered, and then they are taken apart, executed somehow, and it misses the integrity of the original design. But now we have the new tools, the CNC tools, and as designers we can be makers as well. So having the making in the design process becomes one of the most important features of today. To put our work in context, I can also have some points of critics on colleagues. This is OMA. So when OMA thinks they have to make variations, they have 100 students or trainees, and they make variations on one tower to reach this goal, to reach that. So is that parametric? No, it's not. It's just a waste of time and work, I think. So the way I would like to approach it is to have one system where I can tweak all the points, all the vertexes, just like it's also designed for a tower, exactly similar, with a completely different attitude. Then I write a program where I can tweak all these points. Probably because this came too close to this, but I'm not sure. I won't do that again. So I can tweak those points for all of these floors, and while tweaking, this is my target value. I need to make 20,650 square meters because that is what the project developer wants. Disappoint him. I want to give him exactly that. But I also have my freedom in tweaking these lines and all these points and having the curvatures. And I can exactly keep track of what I'm doing. So that process has led to this design, which is exactly 20,670 square meters. And the interesting thing here is also that in the process, things change. So for example, in 1 week before we had to submit for building permit, there was an extra elevator planned inside. So we had to pump up the whole volume again to reach the same GFA, because the elevator is not in the GFA. So we had to pump them and tweak all these curves again, and we did that whole work within 1 week. So we redesigned the whole design because it was a parametric system, because it was consistent, and all the parts were related to each other, we could do that. So this is important quality or potential of parametric design, that you can have all building components related to each other in every stage of the project, from sketch. Well, I cannot do any lecture without showing heroes. Well, this is one of the heroes. And you can see what he has in his mind. This kind of landscaping. He's here at the age of 100, I think. And well, then you can also see some other things. He has these curves, but these curves are not perfect. It's actually a rough technique that does not allow to have sketches, these sketches, directly translated into buildings. And that's what we try to do, and that's also very much in the way we work together, that we want to have intuitive approach, directly related to how things are made, with the precision of the new technology. Those examples, it's not an example of what we want to do, but it's an example of that intuition plays a big role in architecture, and they actually, in almost the same period as we started doing that, they also initiated that. So this was almost blind sketching, and then translated later, but not via CNC machines, but via a shipbuilder who could do that. Actually, we worked with the same shipbuilder later. What we did, actually quite before, or this is actually Ilona's work, sketching with the computer. So very fast, intuitive sketches leading to work, this is works of art, which are derived from those intuitive sketches. And that was fascinating, because there we had the speed of the computer, and we suddenly could relate to that very fast speed of the computer. We are very slow with our brains, but we suddenly could relate to that. And suddenly we could find a link between the computer and intuition, between intuition and logic. And of course, our steps, our first steps, were very small steps together. And finally, step by step, we went to that whole body, had to actually manipulate the whole body based on the intuitive gestures and acts. So this was our first project realized, and actually we wrapped a sketch around as to alienate, actually it's a 6 housing project, as to alienate it from its content. Because what we wanted to do, we want to clean the facade first, empty it completely, and then actually add another quality to it which has nothing to do with the function. And that was another important step we took. And of course it does function. You could slide doors open and put your car in there. So it was a very pleasant way of living, actually, in this patio housing in the middle of the city. So this is another example of those power lines, actually, that's how we call them, these intuitive gestures. They can constitute a building, eventually. So it's one gesture, and we already have in mind that it's becoming a tower, and that's becoming a bridge, and that's becoming a canopy-like structure for a bus station and a restaurant. So we already have that in mind, and we make the sketches, and then these sketches become exactly the basis, very precise, for the later building. Then we construct surfaces, and we pop a network or with points or what we do. This one has not been built. Another example of an intuitive sketch directly translated into a building. And actually the interesting thing is you can just do this. There's nothing which stands in the way to do this. You can just do it. Of course, we have to find a system how to build this, how to build components and how to connect components to each other. And of course, here's another system embedded in it. You have to think of that component and the others. How do they connect to each other? That kind of for today's architecture, I think it's not so much the isolated things themselves, but how they connect to the other. I think that is some of the basic things we are worried about these days. The essence of how we operate. How we operate is very much like procedural work, procedural painting. So generating sketches is already a procedural act. And the way Ilona did it, for example, was making hundreds of sketches and in 1 or 2 seconds, very fast. So what Jackson Pollock was doing is also very procedural. It's a method. It's very methodology. And that is very, very interesting because it is so close to scripting. And scripting is something I will address later, which is then the technical basis for the procedure. And well, you keep on doing this, and it's very clear that these were very simple rules based on this system. It's very systemic. It's also very intuitive. And these two are interesting to join, systemic and intuitive. And so it's very simple in its rules, but in the end, it's complexity in its most essential form. So it's not complicated, it's complex. And that's the big difference I want to emphasize tonight. I don't like complicatedness. So, because it's a lot of work. And then, so if we refer back, for example, we just discussed a morphosis building. That is complicated. That's a lot of work because it's inconsistent in the way how different components relate to each other. They clashed more or less to each other instead of that they arise from each other. It's much different from this. Although you may say this is something like chaos, it looks chaotic. It's not. It's very procedural, it's very systemic, it's very controlled. Another control freak is Frank Stella. And well, we like this work a lot. So in the 90s, early 90s, we looked a lot at this kind of work. Also, you see here in the textures, it's completely procedural. How these, these gestures are actually put on the aluminum here in this case, or there. It's even better to see. But he combined that with these ugly cones. And this, which I hate, because these are platonic volumes, and that's exactly what we don't like. But at the other hand, it had huge qualities because he painted into space. So, and that was another huge quality because painting was always flat. And now he painted into space. Yeah? Still on surfaces that were placed in space, but actually the idea was brilliant. And that's also why he called his book Working Space, by the way. It's this working space, enlarge, expand his working space of a painter. I think it's very important work. Another originating sketch from Ilona was the basis for a landscape design. Actually, we wanted to develop a large area, 7 to 9 kilometers. It's in Almere. It was on invitation to do an art project. It was not an architectural project. So we chose this as a site for actually procedural landscaping. On the basis, we needed a driver for it. So Ilona made many polynuclear sketches that had, in one gesture, had more centers. And then we mapped actually this, or we could say embossed it on the landscape, and the landscape in itself had these polder structures. all these plots were already there. And we gave them all a number, so it's a database, basically. And then, three-dimensionally, this sketch was pushing the landscape up, and other places it was actually bringing it down in a sort of ground balance, that no earth should come in. Then these plots started to develop into different colors, different functions. So it's a combination of the grid city, basically, like San Francisco or any American city. It's a combination of the grid city and a top-down act, a top-down gesture. The top-down is informing all these plots, but in a very specific specific way. And at the same time, there's this bottom-up grow from the grid city. So this balance between top-down and bottom-up became one of the major features of our work. So this was done in 1998. And also we introduced dimmable lighting, street lighting, that it's not always the same level, but actually you can play with it at lower levels, higher levels of lighting. And actually this was very much predicting LED lighting technology as of today, where we can exactly do that. So looking at colleagues, Winnie Maas and VRDV, this is what basically Winnie is doing is his legalization, so to say. He has thousands or millions of these Lego blocks, and the theme of him is porosity. So I want to actually position our work in relation to this by making two statements. His building block is always the housing unit, it's the block itself. Our building block is a building component, which is much smaller than that. The other statement is, this always will remain low resolution because of that size of the building block, and it will never be able to expand the language into high resolution. Yes?
I'm just curious, you mentioned sort of like
where are you? Oh, all the way there, yeah.
The gesture, the sort of intuitive sketch, kind of, it seems to me like, I'm just wondering what gives that privacy as a motivator?
Privacy?
Why do you start with just the gesture? What gives that its validity as a starting point for design?
Well, I have more examples of that. I need information. If you design a system, the system needs information from outside. Otherwise, it doesn't live. So it feeds on information that's coming from outside. That is true for any human being. I mean, your brain feeds on information from outside. Otherwise, you're veggie, so to say. You cannot do anything. So your brain is connected to all the other brains. That kind of relevance is always there. In any design system you have, you need information from outside. And this information actually drives the character, to a large extent, the character of such a system. The other part is bottom-up, what is emerging from the system itself. So these two forces we want to play with. And radicals, as Dutch designers always are, we radicalize everything. We do an extreme point of view of external information, which has nothing to do with logic, but has a lot to do with intuition. And this intuition we can feed into the system. And that idea I like very much, that it's not a logical idea that has to feed a logical system, an intuitive idea, so that we radicalized, so to say. The other important issue here is that we don't start with a function, but we make buildings that allow the building to function, which is a different point of view than that you start from it. It's open for functioning, but it's also open for something completely irrational. So, for example, in contrast to what the Y Factory at the university is doing, this is what our students are typically doing, but it's just one example. It has porosity, it has the same airiness that actually all architecture that is at the front, at the forefront of architecture. It's porous, it has a lot more air, and it's quite different from the agenda of sustainability, where you want to be as compact as possible and have as least connection to the outside. But actually, if you have a good quality of all these skids, you can do it. And then it's no longer an issue. And it's high resolution, so that's the other thing. So this is, for example, a sort of in-between step we are taking with our office. It's a climbing wall system. It's very systemic. It's open to information from for power lines from our side. It's open for interventions by climbers themselves. It's an open design system. It has the building components. It has a higher resolution than the living unit. And you can build anything with that. So that's actually the translation into practice of that attitude. So then we talk about resolution. So it's basically, this is an OMA project. It's again that low resolution attitude, which is very similar to what happened in the 60s and what happened in Montreal in also the 60s. As opposed, just to make clear, just to clarify positions, different positions you can take in architecture. So you can take either that position or you can take another position. This is one of our designs where we have a very high resolution actually in a roof. It's an underground project, and there it becomes a landscaping exhibition hall. And it's all based on that building component that actually can also become larger, and then it can shrink and expand. It's a complete parametric system, and it's completely moldable. That is higher resolution. As high as we think now it's feasible. You can also go higher in resolution, in fashion, for example, and you see a lot of developments actually in architecture that go even higher and higher in resolution. But there's a difference between fashion and architecture. So I suggest, as an architect, if you make models like this is 3D printed fashion, by the way. It's a Dutch designer, Iris van Herpen. So the representatives of Dutch consulate would be very familiar with this work. It's worldwide known. But it's different from architecture. So we should not make the mistake that this can be translated directly into architecture. But it's higher resolution. So this is a kind of resolution we are working with our Hyperbody group in the TU Delft. This is a building block. It's fully parametric. It can take any shape, but it's always related to its neighbor. It's almost like, and that's the comparison I often make, it's almost like this is a bird, and that's another bird, and that's another bird, and together they work in a flock. And they always are measuring the neighbor. They always are, this reference point is always questioning that reference point here, which is the point of gravity. Where are you? What is your distance? And that is the kind of thinking we are completely immersed in these days. And I think that is a very good way forward for a next generation building to think like that. We have to change the very building blocks of architecture. That's basically the message. So don't think bricks, don't think prefabricated housing units, but think of building blocks that are fully parametric, fully controllable, both by your top-down design acts, radical or not, or by systemic emergence from the system itself.
I also use an approach like that, where maybe you have a series of points and they all relate to one another.
Yep.
But when the purpose of it is just to manifest a form that you sketched out, that's where I start to lose you, because I can see a purpose, a valuable purpose, being cutting down on material waste or creating some sort of unique lighting situation for a unique program. But when you instead stop looking at function and just make a parametric system to realize an intuitive sketch, that's where I start to kind of lose you.
Well, there's more to it. So stay with me. You will find out. There's more to it. Okay, the point I want to make here is that, okay, we have these swarming elements, but some elements may be a window, or some elements may be a ventilation unit. Some elements, well, not indicated here, but you have to imagine that. Some elements can be a heat or a cooling unit. So we can actually, and maybe that's already a sort of answer to your question, we can assign functions to each of those components. And all those functions together, they form a climate, a space, a building that functions according to a pre-requested program, etc. So that's how we can work with it. But whatever happens, the relations, and that is what actually I wanted to say, these relations must always be kept intact. Don't lose the connection. And that's, again, the connectivity point I want to make. It's always about connectivity, both in its meaning, in its construction, and in its functioning, its operational life. Okay, what you see here is the construction of that climbing wall. You see first reference lines. These reference lines are, the system is an open system. So what happens, for example, that some of those lines are curves that we like. Yeah? We as a designer think, okay, it has to be that. Other things you see is that there are sort of sloping things in the climbing wall that climbers like. So climbers like a challenge like this, like this. So that is the input of the climbers in this open system. So that's actually how we did it. We sit together with climbers. We have our own preferences for curves. We sit together and they may tweak the curves as well. They may tweak the model. So they become co-designers. It's an open design system. That's what I like. And then it has to be open to all sort of ends, all sort of threads where you can actually pull the strings and you weave all those strings together to make your project. Skin is an important issue, but not separate from structure. I will show you that. First, skin as such, skin of the water pavilion. So it's new materials. It has a new quality of a skin. This is a very rough skin of the water pavilion. It's polyurethane. It's okay. Spend not too much time on each individual project. This is skin of a vase project that we did. It's a vase. You can put flowers in here. These are built-in tubes. You can put flowers in that soft body of the vase. So that's the soft skin. This is an electronic skin of the interior of the transport. Well, you should see it as a movie because everything can move. So these are fixed and these can move, these sizes. It's the aluminum skin of the TT monument that we made. So this is a 2 centimeter thick skin that is bearing all the loads and transferring all the weight to the ground. It's a shell structure, but it's a complete landscape. So if you zoom in on the monument, you see things like that. Another form of skin is this skin for the eye web, which is the second life of the web of North Holland. And then this is cold formed highlight, which is 2 millimeter thick. It's a very thin, it's almost paper. And then, well, weird details as to adjust all the different angles to the structure. But there's always a parametric relation between this component, the connector, and the main structure. Everything is in one system. So it's not like you see, for example, in a Gehry building, there you see, okay, you have the exterior wrapping, you have the interior plaster walls, and in between, a big space, you have somewhere a steel structure, which to Franco Gehry is completely irrelevant how that is designed. For us, it's completely relevant how that is designed because we want to have a parametric relationship between the structure and skin. It's not separate things. That's also why you cannot tender it separately. So as I said, we take very small steps, 1992, wrapping the volume with a dazzle painting. Later, it's not our work, this is in Linz. Later translated, these dazzle painting things are translated into electronic skins that are mapped, and you see that so often these days, that actually skins are mapped on a volume. So yesterday we saw, for example, the De Young Museum of Herzog de Meuron. Basically, it's a very traditional building, how it's built, and then it's mapped with this copper, I think it is, this copper skin. This very nice, I must say, very nice skins, inward, outward, these punching, and sometimes with punched holes, very delicate detail, but it's basically a fashion. This is also a fashion. Very good designers from Austria, Meisel, and what's the other name? Difficult to remember, yeah. If you look at this, it's a great building. It's absolutely great space in here. But if you then look at the structure, so it looks as if I'm criticizing everyone. That's not the point. That's not why I'm saying this. It's that you're pointing out that you can have a different attitude. You can choose your attitude, what you want to do. If you see this structure, it's a mess. I simply have to say, it's simply a mess. It can be anything. You see all sort of hybrid, even in the steel itself, all sort of hybrids, and then strange mixtures with the concrete. And somehow, this happens all the time. It happens to Zaha Hadid. It happens all the time. You see this fashion around it, and you see this very traditional structure inside. And even, which is weird, that this structure, which is absolutely able to bear its own load, it's supported by these. It's not right. And I'm absolutely sure that she doesn't really want this, but this happens if you don't integrate the way you structure it, you construct it into your design process. If you don't relate it in a way that it cannot be taken apart. Well, it's clear that it's like a drapery, like fashion, and that it's very difficult if you start like this, and that's another way it's actually for the person in the end. If you have this intuitive design approach, which Zaha Hadid obviously also has, if you don't connect it to your design system, how it's built up, Patrick's part, so to say, then if it's too loosely connected, you lose that connection between this skin and the structure that supports it. Okay, let's see how we try to do it. So all we do is we try to do what we think is right. And that's also typical Dutch, by the way. That's our... But, okay, I cannot change that. So, and it was orange too, but it tastes like lemon in this case. This is the cockpit structure. This structure is completely in sync with the skin. It's developed together, and if something had to change in the skin, some of the dimensions, for example, glass dimensions, you have to cut it in a certain way, and you cannot extend certain sizes. You have to change the structure as well. So everything is related to each other. And it's a building kit. It's IKEA. Basically, it's IKEA. You have some of these components. They're all different. So in that sense, it's not IKEA at all. So it's parametric IKEA. So you have all these components, and you bolt them together, and surprise, surprise, you get your building. It's that simple. And you can do it, well, you have these one-person offices. They can do it, because it's that simple. If you build this relation properly, then you can bypass contractors. This building was not built by a contractor. It was built by a steel manufacturer. You can have a direct link between you and your design system and the one who makes it. And yes. well, there's a lot to say about this, but it's also used for movies. It's a very nice space inside. It is a showroom for expensive cars, like Rolls-Royce and Bentleys, Lamborghinis, but now it's taken over by another guy, and he sells Lexus. I'm not sure that's the proper one. Okay, let's have a look at another aspect now. We have talking about these building components, the relevance of that, so I have more about that. But first of all, and that was the first chapter in the book, tag that body. So these are identities. All these points, it's a universe of the internet. All these points, they are tagged because your computer has an IP address, has a unique number. So what is now the case, that all of these components your building is constituted of, they need this unique number throughout the whole process. Chapters of a book, they have this unique number, and they have this unique relations to others. But this is maybe more interesting, and it refers to that Hyperbody project I showed you of this building component. So think of all these players. You have these, they are similar, but then you have the other type. Here, these, the bigger ones. And they all have their functions, but together they form a relationship. Together they form interacting swarms of different components. That's exactly what they do. And then you have this type, and then you have the people that walk. It's all mixed. Well, of course, this is Bombay. It's all mixed. That is how it works. But it's fantastic. And this idea of interacting swarms of building components would be interesting to investigate for future projects, for the next generation building. And then look at birds, for example. This is what you know about a swarm of birds. This is actually the typical image. But this is more relevant, I think. This is also the swarm of birds. It's the same swarm. But they are informed by this power line. So that's another answer to your question. So how weird is this? How irrational is this? Why would these birds forming the swarm suddenly sit on that power line? It's exactly as irrational as this digital or intuitive sketch that is informing the design system. There's no difference. You got that? Or
that looks pretty nice to me. Yeah. It's a system at rest. But the previous picture, I would argue that's highly inefficient. It's multiple swarms that conflict with one another and ends up creating a situation that is...
Yeah, but it works.
Just terrible.
It works.
Yeah, maybe not a bird.
Have you been in Bombay?
Well, this looks nice.
Yeah. Well, you're the order guy. Yeah.
Sure. Right. Yeah.
Yes, slowly it went. Okay. This is the acoustic barrier. So we have, no. This is the cockpit. Back to the acoustic barrier. First we have this swarm, but they are already nicely aligned with the power lines that are imposed on the system. So then we have these aligned points, which are the bursts, and then we can run our scripts. We can run our scripts that exactly describe where these points are, what their relations with the neighboring points are. And from those points, we develop the detail. Then we expand the point with all sorts of sub-points, subsets of points that actually, in the end, describe the detail. So this is how we did it with the cockpit in Pro Engineer, another program. We have all these points actually driven by a mother curve, a law curve, so to say. So there is some sort of law and order here, but it's radical, it's irrational. It's driven by that. So we have all these numbers, all these points, and related in this network. And, oh, I don't have the next image here. Okay. I have to change the story then. into this project. Yeah, I'm so tired of these linear presentations because I want to jump, and I cannot jump in this PowerPoint presentation. So, okay, this is all the data you need to build it, and driven by what I already said. You're driven the angles by the climbers and the curves by the designers. But this is about the scripting part. I want to talk, yeah.
I wanted to mention, I think the difference between the chaos and the order is Bombay population is half of the state of California.
Yes.
So 2 Bombays is the entire state of California.
Yes, I think so.
Would it work if we use the logic of our cities versus that chaos theory?
Yes, answer is yes. You asked for it. Well, basically, what I think we have to learn to deal with masses of data. We have to find a way. So there are many ways. So you have, for example, the other Dutch guy, Winnie Maas, Datascapes, works with massive amounts of data. But the other thing is, what does this piece of data represent? And then I want to go in a higher resolution. And well, but the essence is we have to learn to work with massive amount of data. So it's not interesting to think of 1,000 points. No, tens of thousands, millions of points are actually all the reference points that are describing your environment. So the relation with Bombay is evident. Yeah? Millions of points, millions of people, millions of this or that. That's how we have to, that's why we have to work with. We have to find a way to work with that. And you cannot imagine this with your head. Your brains are too slow. You cannot imagine how things rotate in space. It's impossible. Your brains are not fit for that. So you have to find a way to cooperate with the speed of the computer. I think that is one of the bigger tasks of today. How do we work with that? Not as a stupid device, but work with that in the design process and enhance, expand your design possibilities. Well, I see that as the challenge. Water Pavilion, that's where we started, with actually having curves, the power lines, having the reference points, expanding the reference points to subset of reference points, describing everything. We didn't make a drawing to make it. So forget drawings. It's about scripting. And scripting is exactly precise. And we, of course, scripting relates to the manufacturing, to the CNC production, because the machines, they read the data. They don't read drawings. So drawings are only actually for your building permit that someone can stamp it. That's the only way where that drawing still exists. Well, more data coming in from sensors, informing the light environment in the water pavilion, always changing according to that emotive vector formula, which is, again, completely irrational. Scripting, like a sort of game for urban design, where we can play with all sorts of parameters that are connected to those objects, and objects are connected to other objects, and there are attractors that actually are aligning objects, there are repellers, etc., etc. So everything is related in a parametric system. And in the end, you can have a direct translation into architecture from that parametric system. So now we come to that component level, which I keep emphasizing. This is an example of, and that's another name I have so difficulties to remember. That's her. That's her. Yeah, yeah, that's her. I think these are quite repetitive, these components, but what I like is the airiness and the lightness of it, and there's a relation with the structure, by the way. That structure is not exactly correct in its execution, but I think it's a big step forward. Another way of thinking of components is, of course, this what's the exact name of it? Quadcopter. The quadcopter actually picking up the stones and placing them one by one. Well, you all know this example. So also in the assembly, well, this gives the promise that also in the assembly phase, it's important to have an identity of each component and identity of the relation with the neighbor, the exact position of it. But of course, I would never choose bricks to work with. I would make my components as unique components and then have the quadcopter placing these components. So what we do here in Hyperbody, in my research group, we have 4 giant robots. And we have this as basic material, and we use something like this, which is a hot wire that can actually move in space and can describe all sort of complex forms, but still linear because it's a wire. And we also have that with a diamond cutter for harder materials. And then we can make things like this. Then we can make this as a building component, which in itself is complex, and which combines to other components to form the structure. Well, back then, to a simpler component, then explain how things are everything and all the connectivity to other components is actually embedded in one component already. Okay, so all the shapes are different of that climbing wall. It has one central point from where all these other points, which are necessary for applying these climbing grips. And if the triangle is different, also the pattern of this is different. It's aligned with it. And then we go to the other side, the back side. So this, everything is 3D milled. Oh, the side of this, you have to realize that the side of this triangle has a twist, because the shape is doubly curved. I mean, everyone who has worked with doubly curved surfaces knows this. If you have a weight normal on the surface here, next point you have it here, there's always a twist between those two weight normals. So how do you do that if you want to have a smooth surface? Then you need to go from here to here with the milling machine. It needs to follow that twist. This doesn't need to do that, but it needs to be adjusted in its base, such a way that it can be connected by bolts to the next one. So all the connectivity is in a parametric way, in structure and skin, connected. No, I don't have that image. So behind this, behind the scenes, you have all these connectors. You connect here. And the interesting thing here is that we don't have structure in the node. We have it here, and then it transfers the forces through the skin to the next connector, etc. So the whole thing is very, skin and structure are working structurally together also. Well, there we have this. And there we have reference to nature. And that I show actually to emphasize that we never work from nature as to copy it. I mean, I think that's the wrong way, the wrong attitude. So what we always do, we develop the system, and we develop the project, and afterward it looks like something that you know. And then it looks like a whale, or it looks like a big snake, or it looks like, yeah.
With the climbing gym wall,
yeah.
Were they able to remove components and replace them
yes,
with new ones?
Exactly. That's the idea. Each individual component can be taken out and replaced by another one.
To create higher levels of difficulty? Or
yes, that's exactly the idea. That's also true for the cockpit. You can always take out one element of the structure, and all the forces are bypassing that hole that you are making. So it's structurally sound, it's structurally robust. Robustness is actually a very good word for this. And that's also done on purpose, of course. And if you calculate, that's another thing. If you calculate a diagrid structure compared to a rectangular structure with how do you call these crosses? Bracings, I think. if you compare, then this diagrid structure uses less material than a traditional structure because of its effectivity of transmitting the forces to the ground. Well, this has another completely other reason to show you. There's not much non-standard about this. I mean, it's almost completely standard, all the materials he used, but some of the claddings are done in a non-standard way. But actually, most shocking, I find this. When you enter a Gary building, it's such a platitude, it's such a banality. I'm sorry. He's American. But that's not what I am saying. But you take this right from the catalog. All these things you take right from the catalog, and somehow you have to chop it or adjust it to make the shape. So I think that's not the proper way. Again, I had the Calvinist way of saying it. That's not the proper way of doing it. I think you have to make your own catalog. That's the most logical thing. You make your catalog and your building, the set of components you make your building with. So this is the Web of North Holland, and even the door is part of that catalog. So it's not that unique catalog. It's not something you take from somewhere. No, you make it. And then the only thing that this door makes it different from this structure is basically the hinge. It has the hinge, and therefore it's a door. Not very unsimilar to car design, where you have a door. When the door is closed, it forms part of that body. And the only thing where it makes the difference is really these pistons up there and the hinges. So that's where we come closer to making products, housing products, house as a product, where you can actually tweak all the vertexes yourself. This is a project that has not been built yet, where the users can tweak all the curves as to adjust their own shape. And that is done through a website. So we already built that in 2000. So you can tweak all the curves. You can see the feedback here, the curves, roof, other curves, sizes, pump it up. And the interesting thing, it's still our design. So it's still our signature, but it's also open to users. That's also their signature. So we become co-designers. More examples of that. Let's quickly go to this. This is the basis for that polynuclear landscape design I showed you before. That's the plot, and the plot has that potential of bottom-up grow emergence. Well, it's very obvious for you as Americans that the plot has that potential. I think it's brilliant. Grid cities are brilliant. So that landscape has the potential to grow from there to, but maybe there is one step more we could do, and that is in another way play with and that's an attractor game we have written in 1997, play with parameters, as to play with the sizes of what you build in this landscape, and play with the cubic meters of water you want to build. So register everything exactly, play with the number of trees, and then make this public spaces, make these combinations, but all based on an exact calculation of how much you have. So this approach could be combined with gridded cities. So for these areas, playing that design game, you know exactly how big it is, these domains for living. And here it was interested to have the ecological corridors in the housing areas. With this as an end result of an urban design for 1,500 houses. And then back to the individual house inside those housing domains. And everything was layered. So if it was water, then this house was in the water. This is also a very typical Dutch approach. We build more and more houses in the water. And if there's no water, we make water to have houses in the water. So the unification is important. This is the facade of our first housing project. This is the patio houses where we have the dazzle painting wrapped around it. So it's a very simple project. But this is how it communicates with the world. It has a number, it has a phone, and it's a letterbox. If you close the door, if you open the door, it's completely open to the world. But about to unify the project, so this is the unification of the water pavilion. It's all in one material. It's everywhere the same, except here for the panoramic window. Also, the door, of course, is an emergency exit. It's somewhere there. You see the same approach in the De Young for Herzog-Timron, exactly the same approach. It's one material which covers everything. Of course, these developments are always preceded in art. You almost always see that everything that we as architects do is preceded in art. So I'm not tired of that, so we can learn from that and we can cooperate with artists. And the other thing is that technology that we as architects typically use is always preceded by product design. There's always making use of machines way before we as architects use those machines. In other words, architects have the tendency to be lazy and very slow in catching up with new realities. So both from the art, both from the, say, the intuitive side and both from the technical side. But we are learning. Now, also, therefore, these images are so nice. This is Dubai, by the way, but it's so nice because it's unified by the fog. And then back to our own work, that's what we try. We try to unify the overall image, to have it radical, to radicalize that image. It's not different from Herzog-Timron. It's the same attitude. Okay, the other aspect of when you identify all these individual components, all these reference points and the connectors between them, and you can go lower and lower, or higher and higher in resolution, you can also actuate them. If you can do that, if you can identify them, you can also tell this point to move if the connector between this point and the other point is an actuator and not a static one. So that was the basis for this project. It was the design for the interior of a space station, the space station up there, to have one skin that is fully programmable, and you can program this space to be different things, to be a working environment, for example. Computer is very slow. Working environment, that you have sort of a table, or you have this other environment, playfulness, or this is the play environment. So you can have these different modes, basically. Computer is now very slow in responding. Next. You can have these different environments that actually accommodate different functions. So this is another way of telling that it makes sense to identify and to think of the component level and have the emergent modalities from there. It does make sense. And also this environment is completely informed by what you want to do. So it can also be informed by functions, by activities. Project we did with Philips, it's called iLight, intelligent light. These are tiles that are intelligent. They are connected to the neighbor by magnets, so you can take them apart. and you can place this tile, you can place it elsewhere here, and then actually it has a circuit, a board inside, and this, it has a small intelligence, and then it's looking at its neighbor, and basically ask the neighbor, what is your state, your color state in this case, and then it negotiates with the neighbor, and then they negotiate to become similar, to adapt to the other state. So you can see things happening here. So it works. This style exists. It was experimental phase, but it's not on the market. From car design, this guy, Chris Bangle, BMW designer in the first decade, the zeros of this century for BMW, also wrote a book which is very interesting. So that's why I show this title. Have you ever seen this? It's interesting. You should read it. It's a fantasy about what cars could be, well, say after 30 years. What is a car after so many years? And basically he fancies that cars are no longer this complete body, but actually is made of different components that sort of are looking for each other. So there are a set of wheels there, and there are some upholsteries there, and there's some other parts there. And if you need more wheels, then these wheels would assemble to form that kind of car. So it's much more adaptive in thinking than the cars we have now. It's either this car or that car. But then you could think of cars that could adapt to different functions and different needs. And one of the prototypes he made was this one. It's the BMW Gina. And I think it doesn't run out of itself here. So just have a look what is happening here. So the feature lines, the other irrationality in car design, I mean feature lines, it's not exactly for streamline, but it's for building the character of a car. These feature lines can move. So you can actually, as a owner of the car, you can tweak these lines yourself. You can actually customize the feature lines of your car. I think it's a great idea. And aesthetically, this prototype has been the basis for the whole BMW 5 and later 3 series. So aesthetically, it also has been the basis for the design. So what we've fancied almost in the same period is, suppose you have this building. It's a big, you can see how big it is. It has this three-dimensional skin connected to its structure that is actually composed of actuators, of big pistons, electronic pistons. And you need those pistons that know exactly where they are, so that you can give feedback to the system. If you compose your structure of these pistons, it can expand and shrink, and you can adjust your building to different functions. So this is another idea that is actually quite valid. It sounds a bit far-fetched in the first, but you will see actually how much this has been actually creeped into the minds of many younger artists and designers. This adaptivity of structures that you can adjust to different circumstances. And maybe it doesn't look like this, maybe it's much more distributed, like components that, like this project we did with Festo, maybe it's much more distributed, that you have certain components of buildings that behave differently and can respond to the people that are using the space, or just passengers are using the space, and then the walls, this is a dynamic wall, could then respond to you as a passenger. So you pass by here in the base, and there are sensors placed in the base. These sensors no, there's someone approaching me, and then they respond to that. The way they respond, of course, is completely up to the designer, because programming, writing lines of code is designing, there's no difference. Then suppose we do apply that to the whole structure. We also made this test with the Hyperbody students. There's something wrong here. I'm not used to click with the mouse of a Mac. There it goes. You only have Macs here, do you? You don't use PCs. Why is that? You pay twice the money, and you have half the performance. Okay, so here we have the brains. Here it's external in this case. Actually, it should be embedded. The brains are actually calculating everything that is happening with this structure. Here we have muscles, and these muscles can contract and expand. They either relax or they pump up, and then they become shorter. And then people inside are actually playing with sensors that are built inside. Here's also one, by the way, that opens the door or closes the door. And playing with sensors inside, the whole structure starts to have this sort of massage. A good question would be, why would you do that? No one wants to ask that question. Well, that is still pushing almost a button. The other movements are more vague, so to say. More, it's not random, but more vague. Well, there's one very good reason I have for this. That is, if this was a static image, and now it's a moving image, it's absolutely more interesting to watch something that is alive. Yeah? You can compare it to, I mean, here you have a dead bird, and there you have a living bird. You quickly get tired of looking at that one. Well, you feel pity for it. But that one, it keeps it has your intention, so it catches your intention. So it's a very strong thing to catch your intention and to actually become involved in that environment. So there will be many reasons, many applications for this, I'm absolutely sure. I have to look a little bit at time. There is 1 hour, 6 minutes, and 37 seconds elapsed. And, well, I was asking for your endurance, so I suggest 10 minutes more. Is that okay? Yeah, then I have to abbreviate some of the rest of the lecture, so I will skip a few things and then show maybe some projects, some larger projects we have built, to have the feet back on the ground. Is that okay? This really brings your feet not back on the ground, because this was our ground zero project, where we imagined this building, which is multi-story building, and this cube actually contains exactly the same volume as the two towers, and we imagined that building to respond to what happens in the environment. So celebration of the Union flag or something completely different. And you see the building, so you must look at the building there. It changes. It changes completely if there is a complete different thing going on in the city. This is possible. So this was what we did on invitation of Max Protech that was I think in 2002, this exhibition. And actually adaptivity was actually our main issue. So we should not resist and we should not fight, but actually we should adapt and include. Inclusion was actually the main issue. We should include different ways of lifestyle instead of resist to that and fight. And of course there was always one moment that you think back, and this volume could actually become the two phantom legs of the World Trade Center. Well, sorry to be a little bit shocking here, but it's the basis of it is to adapt to changing circumstances. An acoustic barrier that adapts to the train passing by. And the motto for this project is very clear. So now you see it in the relaxed situation. You don't need an acoustic barrier if there's no noise. That's basically the message. So why should we build all those ugly fences around the highways to block the sound if there's not always sound? Well, for a highway maybe it's almost continuous, but for the train it's absolutely not. So once in a while there's a train, and then this acoustic barrier wraps the train as to block the sound and then relaxes again, and can have a life of its own as an art project. It can relax and have some movements, even if there's no reason. Yeah.
Can I ask about the functionality of the acoustic barrier? Because my understanding is the requirement for sound buffering is mass.
Yes.
And the image that you have is fluid, and it seems thin. And
you mean this image that I just showed? That has mass as well. You need not much, by the way, as a mass.
I mean, there may be a new material to be that we may not even have yet that will provide acoustic insulation that doesn't need to be stiff and heavy and weighty.
No, it doesn't.
Right.
It doesn't have to be. I mean, the requirements for our acoustic barrier was you need 10 kilos per square meter. Well, that's this much sand, for example, in a flexible bag. That would do it already. So it's not that much. And that, well, I didn't invent the rules, but that's the rules that were given to us. And that would suit our situation in Holland at all. So I have to skip a few things now. Okay. I think I go to realized projects. Yes, one moment. Yeah, okay, let's start with this one. A smaller one, the Web of North Holland. Structure, the play of light on, well, what was exactly the quote of Corbusier? Masses, play of light on masses. Also from the inside, like hot lava, it's coming from the inside to the outside. This is the design, which is the power line, it's the feature line on the volume. Very much comparable to feature lines from cars. Translated into structure. CNC produced, just to give you a very quick overview of how things are done. It's not that advanced. This is a machine that already existed 15 years before we even discovered that it existed. And then you have to realize that we're 15 years before others discovered that it existed. So there's these big periods of time really have to pass before we get to know things. Then each component is unique, and because it's double curved, many components are twisted. They have these, let me see, where can I show that? Why don't I see that? Strange. Well, okay, well you can see it in this one, for example. But actually most of them are twisted. Oh, not these ones, these are not twisted. To accommodate the curvature. architecture. No, sorry, art, architecture. Yeah, because now it has a function, it has a door, so there must be something in it, so it must be functional, must be architecture. Well, that's the whole difference between art and architecture. Functional use, second use, the structure alone, new detail, in front of the faculty, in front of the burned faculty. This was a tragic moment in 2008. And now that building is completely gone and we are in a renovated old building. Maybe some of you know that. And actually it's a perfect place to work. This was not so good. Yes, I go now to the, let me see, yeah, I think really these sort of facts is good to see. Just go quickly through it. This is the acoustic barrier in the cockpit, point cloud, scripting, not drawing but generating, not drawing, generating the 3D model, generating the exact panels to cut for the glass, generating the exact holes for where the bolts have to come. This is actually a visualization of the structural program of the steel manufacturer. Making it, it's as simple as this. It's just a normal workshop, but it reads data. Making a prototype, always necessary. Identify all the components. Each component has a unique number. Make prefabricated packages of components, bring them to the building site and bolt them together by heavily underpaid workers, I have to say. That is mostly the case, because they don't need to know anything, they only need to know a number, and then putting them all together, and then the dynamic of the shape is formed, and then it forms the shape. So it's very much formation, it's not deformation. It's not like you have a mass and then you make a deformation. No, it's actually forming it. It's a formation. Like the flock of birds is a formation. It's not a deformation. This is Google view, so you can see it. You can see all these buildings on street view. We didn't want to have the acoustic barrier to end abrupt, so that's why we have this feature line, the fault line, and then becoming actually this line that goes all around, and then it continues on the other side. So it has two equally looking good sides to it, not a front side and a back side. The client, happy with the model, physical model, the concept, the node. So this is one of the 300 different nodes constituting the building. Okay, a quick word on evolution. I go very quick now. Separate components, more and more embedded in the body, more and more integrated in the grille, more and more rounding the corner, more and more becoming part of the whole. All sort of lines continuing from here, in the headlight, and then continuing in something that is completely alien to it, but still communicating. And I think that is an enormous progress in body design, and we can learn a lot from car design in that sense. Because usually it's not done in architecture, and I think this is the big future for it. So some of our attempts is a BMW showroom. Well, the Lincoln Continental, that's where I played with as a kid, but now it's important that the Lincoln Continental, the Ford Lincoln Continental, had this ending, actually designed from the side and designed from the top and the front, and this Continental, the Bentley Continental, it goes from the side, it goes to the front, so there's a continuity around the whole body. It's much more a three-dimensional design. So that is actually one of the big progresses we have seen in car design as well as in architectural design. So no more side view, no more floor plans. So if I would teach here, I would actually forbid floor plans, forbid side views, forbid sections, etc., and almost forbid drawings. You see cross-fertilization, that this Jaguar, this unique feature of the Jaguar, this one, this light that actually comes from that curvature from the side, it's actually already pre-conceived here in this Lancia, and then even better, in this Suzuki Swift, it was already there. And it was 10 years before the Jaguar. So this I find very interesting. So completely different brands and how they cross-fertilize between each other. So there must be a connection. Now, of course, some of these designers, they hop from one brand to another, but that's not the whole story. There's much more to it. Well, there are many examples of this. Now I'm going to finish with some of I have to show this as well. This is my father's interpretation of Mies van der Rohe, sort of playfulness. So my father was an architect, so the negative corner. But he was playful, so he had these windows that were more playful. And then 50 years later, that's our own design, that we have sort of incorporated this playfulness, this different sizes also, but we have actually radicalized the corner, and that's actually something I really wanted to show, because that is. So this is the Mies corner, and the radicalized corner. Let me see where I can find it quickly. Oh, it's in the end. Well, it starts here. The radicalized corner. So this is the Liwa Tower in Abu Dhabi. We have been building. So all these building components are unique in size and dimensions, but when they fit together, but it's very robust, as you can see. When they fit together, they form the whole. And they are in sync with the structure of the skin. So you see a very high definition of the structure. It's very dense. It's also very strong. It doesn't use more kilo steel, by the way, but it's denser in its structure because it has to sync with the skin, and usually the skin is smaller plates of raw material where you have to cut the aluminum from and the glass, etc. So that's where they come together, and then they work together. But now this corner problem, which is no longer a problem, reference point inside of structure refers to a reference point on the exterior of the skin. That's one system. And then this is the logic. Then the reference line here somewhere in the middle. That reference line travels. Where's the corner? Travels towards the corner. And you can see here clearly when I'm looking, this reference line is no longer aligned with this. And it becomes, because it sort of travels to that corner, step by step. Meaning that it's not a fixed relationship, but a dynamic relationship between those two reference points. And only therefore, we can have this corner, which is exactly the same detail as this line, and the fault lines somewhere in the middle. So that is the sort of radicalizing Mies van der Rohe, or in other words, Mies is too much, which I used to say. So both because I like him very much, I very much respect Mies van der Rohe architecture. I think it's super, but still he uses a lot of additional details, which is not necessary if you have a parametric system that actually can cater for all these variances, can cater for all these instances. And that's the inclusive approach. So this approach includes the other approach. Also, it includes rectangular architecture in a different way than the traditional architecture excludes this. So that's the difference. So this includes the other excludes the one. And it is called Liwa Tower because the colors look very much like the Liwa Desert, which is south of Abu Dhabi. It's part of the big, the empty quarter. I would put this as an image behind my desk instead of that image of Niemeyer. So now we are coming to the closing section of the lecture, next generation building. That is building from component level imposing all sorts of power lines you want to have on that system. They're working with the robots, the components, working with the intelligence. This is the protospace, by the way, this protospace floor, where all these elements are, these are lights, and these are lighted up by the small brains that are built in here. And these brains, they actually work like that, and that is in ICT technology quite revolutionary. They work as members of a swarm. So this brain communicates with this one. So if it radiates some data, this one is informed and then brings the data to this one, to this one. So it sort of has a viral effect from there. Also, this system can be informed top-down, to start from here and then spread. So it's a combination of working together, and now it's a combination of bottom-up and top-down working together. But it only works if this identified component is intelligent. And then we can actuate such a structure. Then it can actually act by itself, and it can also be acted upon. Mouse problem. Well, then, this was my last, well, actually, no, I have to show the set as well, don't I? Yeah, okay, give me 2 more minutes. I come back. Otherwise, I skip too much. But it's not easy to, yeah. Because it's another example of how power lines can inform a system, and it's also a project that relates to existing old buildings as well. So that's where it started. This building in Budapest, and you see the relation with an old building there. And it goes like this. We have 2 warehouses, and we have a lost piece of a warehouse there. And we have a pitched roof, which is like this pitched roof, and then it transforms and it rises up, and then from the top, the pinnacle of the pitched roof, it leaves and touches the ground and forms a body, forms a volume, like this. So here, behind it, this roof, it goes up, and then exactly at the top it leaves, and then exactly there it touches the ground again. So these are the power lines we enforced on the system as to form a big event space inside there and escalators leading up to that event space. This is then the entrance from the city side. Here you have, by the way, the Faculty of Architecture, which is very interesting because you have some of these old-fashioned traditional teachers here, still in white coats. Remember that? Old days, white coats, and this paper, big tables, and they're looking at this. Very interesting. It's already used as a venue for marriages. Like here they go to the Japanese garden to have their pictures that we saw yesterday. But it's interesting that they choose these kind of situations to make the wedding picture. So that is the traditional part where we have the three roofs. and then it extends into that body part. And here you can see how dramatically the structure actually comes from there and then almost falls down, and here is a dramatic twist in it. But also it forms a very functional canopy to have a dry side entrance. So there's always one more reason to do something. And maybe that's, yeah, if I would have some real message, then I think it's, and that's the, for me, that's the definition of sustainability. Always have more than one reason to do something. So if I build an acoustic barrier, I build a building into it. So then I have two reasons. One is acoustics, the other is I have a building. So if there's more reason than one to do something, it's the most sustainable act you can do. And then, okay, the last image, that was this book cover. That will be a new scientific journal. So this is actually really a new side of the profession of architecture, that we are coming much closer to real science. With the kind of work we are doing, and kind of work many architects today are doing, we come much closer to real science, and it becomes interesting to set up a magazine, scientific magazine for architecture. And I call that Text Generation Building. It will be out end of this year, and I will send invitations around actually to send in papers for that one. Okay, I would like to finish the lecture here. Thank you for your endurance.